Diana, shall we start, Diana?
Yes, ma'am.
Good morning, students. So, today's lab, we are going to see about how to interface 0808 DAC to 8051 microcontroller. And also, we will see about how the conversion happens from digital to analog. And also, we will write some assembly language program to generate analog waveforms like square wave, sine waveform, staircase, Sawtooth, and ramp, okay, using DAC0808 IC, okay. So microcontrollers are used in wide variety of applications like measuring and controlling of physical quantity like temperature, pressure, speed, and distance, etc. Okay. So in these systems, a microcontroller generates output which is in digital form. Okay, your microcontroller is able to generate output in digital form, but the controlling system, that is your external environment, requires analog signal as they don't accept the digital data. Okay, so that's making it necessary to use DAC, which converts digital data into analog voltage. Okay, so DAC is a device or IC that is widely used for converting digital pulses to analog signal. So there are two methods of converting digital signals to analog. One is binary weighted method, other one is the R2 2-hour ladder method. So in our experiment, we are going to use MC1408 IC. MC1408. That is DAC0808. So this IC uses this R2 LiDAR, 2R LiDAR method. So this method can achieve a much higher degree of precision. Okay, and also your DAC performance depends on resolution. That is one of the parameter. So which is a function of number of binary inputs, number of data inputs. So the number of data inputs decide the resolution of your DAC. Actually, most common input counts are can be 8. So your input count can be 8 or 10 or 12, etc. So number of data inputs decide the resolution of DAC. Suppose if there are n digital inputs, okay, that case it can generate 2 power analog levels. So 8 input DAC IC can generate 256 discrete voltage level of output. So that is the meaning, 2 power n. Similarly, suppose 12-bit DAC can provide 2 power of 12, that is equal to 4096 voltage levels, discrete voltage levels. Okay. There are also 16-bit DAC, but they are expensive. Suppose more number of bits ICs are more expensive. So in our experiment, we are using 8-bit DAC. So nowadays DAC is available as a single chip. So the specification of DAC is on full scale output, number of binary inputs, resolution, settling time, and linearity. Okay, we will see one by one. So first, full scale output voltage, the maximum output or full scale output voltage can be 5 voltage or 10 voltage. So we can have the output voltage in the range of 5 or 10. Okay, we can generate 5 voltage waveform or 10 voltage waveform. And next, number of binary inputs can be 4, 8, 10, and 12. And resolution is the number of digital analog voltage, as I said earlier, that can be provided by a DAC. For n-bit DAC, the resolution is 2 power of n. So these are the important specification to decide the performance of your DAC chips. Okay. And next one is the settling time. So settling time is the time taken for the output to settle within a pre-specified band after the input digital value is applied. Okay. And linearity is the one of the parameter. It is a measure of how straight the output is when the input is changed from minimum to maximum. So here settling time is the important parameter, important specification, as the DAC output may overshoot the current value and oscillate for some time before settling. Okay. So your full scale output can be either 5 voltage or 10 voltage, and number of binary inputs, that is, it depends on your digital inputs, and your resolution is equal to 2 power of n. Here we are using 8-bit DAC, so 2 power of 8. So we can have 256 analog discrete voltage levels. Okay, and also we can give 8 digital inputs to DAC chip. 8 digital inputs. So it is a 16-pin 8-bit monolithic DAC, that is digital to analog converter, featuring a full-scale output. Current settling time is 150 nanoseconds. Please note down the important parameters. And also while dissipating only 33 milliwatt with plus or minus 4.5 voltage to plus or minus 18 voltage. Okay, so these are some of the features of DAC IC. So here the important thing is DAC can directly, that is directly interfaced with TTL or DTL or CMOS logic. So we can directly interface this DAC with 8051. Okay. So this DAC IC has no internal command register. So hence it is directly interfaced to the port bits of 8051. So there is no control signal. Previously in ADC we have many control signals. Here this IC does not have any command register or control signal. We can directly attach this IC to 8051. So whatever value we are converting, that value should be sent to this IC through this port. Okay. So based on our bar 2 or ladder network, the conversion operation is performed and output will be placed at the I out. Your output signal will be I out. This is the I out. Okay. So there are 16 pins you can see here, this diagram. So pin 1 is the not connected, and pin 2 is the ground pin, and pin 3 VEE. Suppose if your voltage is plus or minus, so it is a dual inline package. It requires dual power supply. Suppose if the voltage is plus or minus 18, here you have to apply minus 18. And V reference plus 18. It can be grounded. Negative reference can be grounded. Here you have to apply plus 5 voltage. So this is about your power supply details. Suppose if you are configuring this circuit for plus or minus 18 volt, means the minus 18 volt should be connected to VEE and plus 18 should be connected to positive V reference, and negative V reference can be grounded, and plus 5 voltage can be applied to VCC. So this is the power supply configuration. This is about your power supply configuration. Okay. And next, pin number 4. This pin number 4 is very important. It's an analog output. So after applying the digital inputs, the output will be in current form, not in digital form. Okay. So here your analog output is available in the form of current. So we need external current to voltage converter in order to convert your current value into voltage form. So external current to voltage converter should be attached to I0 pin, okay, in order to convert your current value into voltage value. And next we have digital analog inputs, that is digital inputs from microcontroller to DAC, that is A1 to A4 digital input, similarly A5 to A8. Here A1 will act as MSB, A8 will act as LSB. Please note it down. And compensation is used to maintain proper phase margin. So capacitor may be tied to this pin, either VEE or ground. Okay, here we have to connect one capacitance in order to maintain phase margin. There is proper phase margin. So that's all about your pin detail. So this is the block diagram of DAC. So the inputs A1 to A8 are given to current switches. Here we have one R2 to our ladder network and reference current amplifier. So this block is the reference current amplifier. So the conversion is performed with help of R2R ladder and reference current amplifier. Okay. So here we have R2 ladder, which is the basic technique of DAC. Also there is a reference current amplifier. This current amplifier is going to provide external reference signal V reference plus and V reference minus. Okay. And also we have NPN current source pair. So the this bias circuit is mainly for biasing this NPN current source pair. And the reference amplifier provides voltage at pin 14 for converting V reference to current reference. So the output of this current reference amplifier is I reference. So that is given to this R2R ladder network. It will perform conversion operation, and your output is this digital input is converted into analog current. So output will be generated at this point. So I'm not going to talk about more about this. If you want any more, that is more details, you can refer the data sheet of this particular IC. If you want more details regarding this block diagram, you can refer the data sheet of DAC0808. Okay. So I out. So this is the output signal of your DAC. So this I out of DAC depends on I reference voltage. I reference flowing into the V reference and the status of all your digital inputs from D0 to D7. D0 is your LSB and D7 is your MSB. So I reference current is generally set to 2 milliamps. Now assuming that I reference is 2 milliamps, and if all the inputs to the DAC are high, okay, so find out the value. So your I reference is generally 2 milliamps, okay. And all the inputs to the DAC are 1, are high. So just you apply the value and find out the I out. So what is the answer? Please tell me. Please note on the formula. This formula is very important to calculate your I out value. So what is the answer? So based on the data sheet, your I reference is set to 2 milliamps. And all your digital inputs are 1. What is I out? What is the answer? Please post it in the chat box. 2 milliamps, that is 1.99 milliamps. So that is the correct answer. So when we are applying 1 to all the bits from D0 to D7 and multiply that value with I reference value, you will be getting 1.99 milliamps. Okay. So next we have to calculate V out. Okay. What is the formula to calculate V out? So V out is equal to I out into R. So assume your R is 5K. Find out the answer. So your answer I out is equal to 1.99 milliamps. When all the inputs to the DAC are high, that case, okay. So next we have to calculate V out. V out is equal to I out into resistance. Assume this resistance is 5K. So what is the answer? 9.95. So that is the analog output. So in this way, the analog output will be calculated by using this DAC IC. So your R2 or ladder network will perform this operation. So based on your digital inputs, this way your digital value is converted into analog value. Is that clear? Suppose if all the inputs are 0, what is the output? When we are applying 0 to all the bits, your output will be 0. V out is equal to 0. Okay. And practically, we are using this calculation I out. For simulation purpose, we have to use this formula to calculate our V out. Okay. So according to the R2R ladder network, V naught is equal to V reference and all your inputs, digital inputs from D0 to D7. Okay. For example, if data is equal to 0, all the bits are 0. And your V reference 10 voltage. So what is the answer? Your V naught is equal to 0. In Proteus simulation, we have to calculate our analog output voltage using this formula. Okay. And next 801000, and what is the output? 5 voltage. Suppose I am applying 1 to all the bits. So what is your output? Your output will be 10. So this is a schematic diagram of DAC. So this DAC design included with 2 chips. One is DAC0808 and other one is the LF351 operational amplifier. So this operational, that is LF351, is the JFET input operational amplifier. Okay. So we will see the circuit connections. Please note on the circuit connections. Okay. So for working of device DAC, that is 0808, we need two voltage sources. One is 5 voltage, next minus 15 voltage. So this is the major drawback of this DAC, so which is eliminated in modern DAC ICs to make them work from a single power source. So we require two power supply, 5 voltage and minus 5 voltage. Okay. So here you are according to this design, the 8051 microcontroller interfacing. So your 8-bit data bus of DAC is attached with 8051 on port 2. So 8-bit data bus of DAC is attached with 8051 on port 2. So 8-bit digital input is loaded into input lines from A1 to A0 of DAC. Okay. So the range, 8-bit data word range from 0 to 255. Since it is a 8-bit port, so the value ranges from 0 to 255. So we can apply the values from 0 to 255 in hexadecimal 00 to FF. So the logic is your DAC, after applying the inputs, DAC converts the input data into analog currents I output. Okay. So for changing the present parameter, that is current parameter to voltage parameter, this LF351 operational amplifier is connected in the circuit. And basically, this LF351 is one kind of JFET operational amplifier. This is an inexpensive device with the characteristics like high performance, provide a high slow rate and a high gain bandwidth, and even operating with low power supply. Okay. So this circuit is known as current to voltage converter. So this will perform, that is, it is used to convert your current into analog voltage. So the analog voltage from the operational amplifier is a linear relationship among the value of input digital. Okay, so in this way, the conversion of digital to analog can be performed. So here we have I to V converter. So this I to V converter is constructed using LF351 operational amplifier. Okay. So according to the power supply connection, please note it down. A negative power supply of minus 15 volt is required for proper operation. So minus 15 volt is attached with this VEE pin. So it is attached with VEE1. And also one capacitance is connected with this compensation pin. Okay. And also this VEE minus 15 voltage is connected with fourth pin of operational amplifier. Minus 15 volt supply is attached with fourth pin of operational amplifier LF351. Okay. And next one, V reference. So V reference is attached with ground through this 5K resistance. As specified in the data sheet, you have to connect 5K resistance to ground your V reference minus. Okay. And V reference plus is attached with 5K through 5K resistance, through a 5K resistance. And also 7th pin of this amplifier is connected to 5 volt DC. Please look at this connection. 7th pin is connected to 5 volt DC, and also V reference positive is connected to 5 volt DC through 5K resistance. So suppose if you are applying 5 plus 5 voltage here, this means your output of DAC can vary from this point, can vary from 0 to 5. Suppose I am connecting 10 voltage power supply here. So the output of DAC can vary from 0 to 10 voltage. So first you connect negative 15 voltage to VEE and also negative 15 voltage to fourth pin of LF351 amplifier. And I out, you have to construct this I to V converter. You connect the second pin of your operational amplifier to I out and ground the third pin. And this will be your feedback resistance. And plus 5 volt supply, you have to connect plus 5 voltage to 7th pin of operational amplifier and also positive V reference, and negative V reference is connected through a 5K resistance. Suppose if this power supply is plus 5 voltage, you can vary the output voltage from 0 to 5. Suppose I am connecting 10, I can vary the output voltage from 0 to 10 voltage. So due to op-amp offset, so the value will be saturated. Instead of getting 0 to 5, we will be getting the value from 0 to 3.5 in case of 5 voltage. In case of 10 voltage, we can vary the value from 0 to 8.5. So the maximum value 8.5. For 5 voltage supply, the maximum value 3.5. That's all about our connection. So here we have to connect a CRO to observe our waveform results. So your CRO should be connected to the 6th pin of operational amplifier. So next we will see about the waveform generation. So your first waveform is square wave waveform. So in the square wave, we have to form the waveform like this, okay? So we have to send the value 0, 0 and then send FF to DAC. So that is the logic. So for some time, send FF. After that, you have to send 0, 0. So what we will do, first we will send 0 to port 2. Then call a delay routine. We will call a delay routine. Then we will send FF again. Then we will call the delay routine. So repeat the steps from step 1. Okay. So in this way we can generate the square wave. So the logic for this square wave generation, it's a very simple. Just you move 0, 0 to port 2. Okay. Call delay routine. Next move either 0, 0 or FF. Okay. Move P2, comma FF. Call delay. And repeat the operation to get a continuous square wave. So this is the logic. Please observe the code. So I'm moving FF to P2, call delay routine, 0, 0 to P2, call the delay routine and repeat the process. So you can see the square wave is being generated at P2. Just you stop this and trace the frequency. So 19.22 Hertz square waveform generated at P2. Okay, so this 19.22 Hertz for full cycle. For half cycle, 37.8 Hertz square wave generated. Okay. So next, load the hex file in the Proteus simulation. Just please note down the connections. So here I have connected all the port pins, P2 pins to your digital inputs of DAC IC. Based on the circuit design, here I have connected current to voltage converter. Minus 15 voltage is connected to VEE, and plus reference voltage is connected to 10 voltage power supply, and V reference is grounded. So at the output pin, I have connected CRO to observe the waveform generation. So first load the hex code. You can see the square wave is being generated. And also so the voltage is varying from 0 to 8.5. Since I am giving 10 voltage here, so it's oscillating between 0 to 8. So if the inputs are 0, your output will be 0. When all the data inputs are 1, means your output will be 8.51. Here the value are continuously changing from 0 to 8.51. Okay. Any doubts regarding the square wave generation? Do you have any doubts? The circuit part and I out calculation part and V out calculation part. Shall we move on to the next waveform, triangular waveform generation? So in triangular way, we have to send the values from 0, 0 to FF from microcontroller to DAC. So what we will do is here, we send 0, 0. Next, we will increment it by 1. First, we have to send 0, 0, and we will increment it by 1 next point. Again, it will be sent to DAC, likewise up to FF. So first initialize the value and keep on incrementing the value till it reaches FF. Okay. So after reaching FF, once the maximum value is reached, we will decrement the value by 1. Decrementing the value continuously. Every time it will be sent to DAC. Okay. After decrementing, it will be sent to DAC. When it reaches 0, again we will increment. Likewise, we have to generate the triangular waveform. So here, first 0, 0 is loaded into accumulator and load that value into P2 since P2 is connected with your DAC IC, and next increment the accumulator value till FF. Okay. So for that, we have to use compare jump not equal instruction. You have to compare your accumulator content with 0 FF. If both are not equal, repeat the same operation, that is increment operation. If both the values are same, next you move the maximum value, load the maximum value to P2 and perform the decrement operation till reaches FF. Sorry, till reaches 0, 0, not FF. Here you have to use compare jump not equal A comma hash 0, 0 and repeat the steps from 2 to 4. In this way, we can generate triangular waveform. Okay. So first 0, 1, 2, 3, likewise up to FF. Continuously, after increment operation, you have to send the data to P2. So after reaching the maximum value, you have to perform decrement operation till 0, 0. Again, increment and decrement. Okay. So initially accumulator is loaded with 0 and transferring accumulator content to P2, perform increment operation till it reaches 0 FF. And next, load the maximum value. That is, now your accumulator holds FF, load that value into P2, perform decrement operation, and each time you have to compare this accumulator value with 0, 0. Okay? And repeat the same operation to generate continuous triangular waveform. Okay. So continuous triangular wave has been generated at P2. So here you can see the output variation. The maximum 8 voltage, 8 point something, around 8, 8.5. Suppose I am changing this voltage to 5 voltage DC. So the value changes from 0 to some 3.5. So your V out completely depends on this power supply. Okay, your output can that is output voltage can vary from, suppose if I am connecting 5 voltage supply, your output voltage can vary from 0 to 3.5. Suppose I am connecting plus 15 volt supply, your analog voltage can vary from 0 to 8.5. Okay. Any doubts regarding triangular wave generation? Students, please respond. Any doubts? Because it depends on your capacitance value. Ma. So we have to increase our capacitance value to get a sharp peaks for triangular. So next waveform, Sawtooth waveform, very similar to triangular. So the only difference is here, instead of increasing the value, we can directly, instead of sending the value 00 FF, we can directly incrementing the value from 00 to FF. Okay. So first, initially start with 0, load that value to P2, increment the accumulator content. So what is the maximum limit of the accumulator? Maximum the limit of accumulator FF. Okay. Repeat the same operation after reaching the maximum value, it rolls over to 0. And again perform 00 to FF to get a continuous Sawtooth waveform. So this is the code for your chart. It's very simple code. First, our accumulator is initialized with 0, moving 00 to P2, perform increment operation. It's continuously, the value will be incremented. After reaching the maximum value, your accumulator is cleared. Again from 00 to FF and FF to 00. So can you identify the difference between your Sawtooth wave and triangular wave? 00 to FF and FF to 0 straight away. So here you can see the maximum value 9. Sometimes it will be around 12, 15 also. So any doubts? The Sawtooth wave form generation. So next waveform is staircase waveform generation. So actually this waveform is constrained between the minimum to maximum value. That is, the voltage levels are divided from 0 to 255 for your 8051 microcontroller. Since it is a 8-bit microcontroller, so we have to divide the voltage levels from 0 to 255. Here you can see the number of small step changes in voltage level between maximum and minimum voltage levels. Okay. So here this 255 is divided into 5. So what is the value? The value is 51. So first you have to send this 51 to your port P2. Next add 51 with 51, 102, 101 with 51, 204 and 255. So the 0 to 255, the range is divided into 5 values: 51, 102, 153, 204 and 255 to generate your staircase waveform. Okay. Suppose if you want to to generate more number of steps in the waveform. That case, you divide that value by 11. So what is the answer for 11? 255 divided by 11. It's around 23. So we can fix 25. 25, likewise 50, 75 till reaches 250. So we can get 11 counts. That is 11 steps we can generate. So here we have to follow the lookup table method in your program. First initialize send 0, 0. Next 25. Next 50. Next 75. Next 100. So the entire range is divided into 11 steps. Okay. 150, 175, 200, 225. Next 250. After that we cannot proceed because the value will be exceeded. Okay. So stop this till 250. Okay. So we have to get the value. First initialize all the value in a particular memory location, get the value one by one and send the value to your P2 continuously. Okay. So the program sends the values to the DAC continuously in an infinite loop to generate staircase waveforms. So the logic is very simple. First initialize your load count. Load count will be 11 here. Clear your accumulator. In order to fetch the data from lookup table, we have to use this MOVC instruction. MOVC A comma at A plus DPTR. So that instruction is to be used here to get the data from this lookup table. So all the values are pre-calculated value. We have to get the value through this instruction and move that value to P2. So after reading the first value, you call the delay routine. Next, increment the data pointer. Okay, and next you decrement the count. So this loop has been repeated until your R5 becomes 0. Once the count reaches 0, you go to step 1 to generate continuous staircase waveform. Okay. So first, initially, your program code starts at 000H and initialize your lookup table starting address to DPTR and initialize the count, clear the accumulator. Using this instruction, you can fetch your data bytes from lookup table and move that value to P2, call the delay routine, increment DPTR, and repeat the loop until your R5 becomes 0. Okay, and this is your delay routine. Here you have to store your lookup table values. After that, terminate your program by using end. Otherwise, your program will not be terminated. You have to use end here. Okay. So you can see the steps, 11 steps, 11 counts. So the 0 to 255 is divided into 11 steps. Okay. So the values are between 0 to 255. Okay. So if you want to add more step, okay, the maximum is 11. Suppose you want to decrease the number of steps, you can divide the numbers with smaller values. Divide your 255 by smaller values. So any doubts? Either you can use lookup table method, otherwise you can define your inputs directly using move instruction. You can directly assign the value, that is 11 values, into P2 instead of using lookup table. Okay. So next one is the sine waveform. The logic of the sine waveform is very similar to your staircase. So similar to a staircase waveform generation, here we need to calculate, that is we need to form a lookup table to represent the sine wave angle between 0 to 360 degree. So we will consider 30 degree increments here. For each points, 30 degree increment. So to calculate the V out value, we have to use this formula. V out is equal to 5 voltage plus 5 into sine theta, and you have to vary the value from 0 to 360. Okay, and each count will be calculated by using 30 degree increment. Okay. So first you calculate 5 voltage plus 5 into sine theta. Next sine 30. Next sine 60. Likewise up to sine 360 degree. Okay. And also assume this full scale output voltage is 10 voltage for DAC output. For sine wave circuit, you have to fix that VDC 10 voltage. Okay. So this is the table, lookup table. So first angles are divided from 0 to 360 with 30 degree increments. Okay. And next sine theta will be calculated based on this formula. So based on this formula, we have to calculate V out. So calculate sine theta first. Okay. And V out will be calculated by using this formula, 5 voltage plus 5 into sine theta. Okay. And the value sent to DAC can be calculated. Actually, there are 250 steps, 256 maximum value, 256 steps. And full scale output voltage is 10 voltage. Okay. So divide this 256 divided by, that is 256 by 10. 25.6 steps per voltage. Okay. So here output voltage is 5. So you multiply this value with 25.6. This is 25.6 steps per voltage. We have calculated the voltage, V out voltage. Multiply this 5 by 25.6, you will be getting this value 128. Likewise, you have to calculate values up to 360 degree. So your program has to send the values, send the lookup table values to DAC continuously to your port 2 in an infinite loop to generate sine wave. So that is the logic of this sine wave generation program. So this waveform is generated by using KEIL Microvision. This is the Proteus simulation output. Suppose to get a better looking, suppose if you want to get accurate sine wave waveform generation, you recalculate this table for 2 degree. So every 2 degree you have to calculate the values. For that case, we can get an accurate sine waveform, exact sine waveform. Okay. So similar to your staircase waveform generation, define all your values in the lookup table and get the values and send the value to P2. After sending the value, you have to call the delay routine. Okay. The continuous sine wave is being generated at P2. So the waveform is not accurate in your Proteus simulation. Okay. So you can recalculate the values for 2 degree. For that case, you can get better sine waveform. So the output voltage can vary from 0 to 13.5 something, around 13.5. So this voltage depends on this power supply. Okay. For this generation, for sine wave generation, you make this power supply is plus 15 voltage, not 5 voltage. Okay. So that's all about your waveform generation. Any doubts regarding your sine wave and staircase wave? So execute all the assembly codes in KEIL Microvision and observe your waveform using logic analyzer. Okay, and also measure your frequency and amplitude and simulate the circuit using Proteus and observe the waveform, and also submit your outputs in the in the Google Classroom on or before next Friday. We need to add hex file from KEIL. So here in options here, just you click this before execution. In output, you have to enable this create hex file option. So after debugging, your hex file will be generated in your folder, automatically generated in your folder DAC. So try out all the codes in KEIL Microvision. So the unique feature of KEIL Microvision, we have logic analyzer. So in sine waveform or square wave generation or any waveform generation, we can measure the frequency and time period more accurately. Any other doubts? Dhanalakshmi?
Ma'am?
The video is project control.
Okay, ma'am.
Okay.
Shall I share my screen?
One second.
Good morning, all. So last class you learnt ADC, and this class you learnt about DAC. So your previous year students, I mean your seniors, would have gone to the laboratory and they would have did the same experiment using the hardwares. Okay, so I'll show the video how to work with the DAC hardware and you're supposed to show the output. Okay, I'll present my screen. So interfacing DAC with 8051. So you are using DAC0800 and it should be interfaced with 8051 using the bus connector. So you can see a broad white connector which is called as the bus connector. So you can interface both your interfacing kit as well as your 8051 microcontroller. Okay, and apart from this, you should have a CRO probe. Okay, and your probe will be having two ends, right? One will be your positive and the other one is your ground end. Okay, so you should have connecting wire in both the ends. Okay, so you are supposed to feed the code. They have they are feeding the opcodes using SP space the starting address. Okay, so SP space starting address, by entering it you can give all your opcodes. Okay, so opcode for the corresponding experiment is given. So they are executing the program now. You have to execute by giving go starting address and by pressing enter, the code will be executed. Now you can see the interfacing board over here. I'll pause the video. So now you can see the interfacing board. So your interfacing board has 4 ports. Okay. So one is FFC8. The first one is FFC8 and the second port is FFC0 and your fourth port will be ground. Okay. So in your probe, you will be having two ends, right? So the positive end should be given to either FFC8 or FFC0 depending on your code. Okay, if you are posting all your values in FFC8, you are supposed to give your positive end to the first port. Okay, if you are posting all your values to FFC0, in that case you are supposed to give your positive end to the second port. And for both the cases, the negative end is common. You are supposed to give it to the fourth port. Okay, so this is the connection uh, to connect your CRO. Okay, so they are giving the connection. So they are giving the connection as I said. Okay, so here they have executed a sawtooth waveform. Okay, so after you connect this and after you execute it in your 8051 hardware, you can see the output in your CRO. You can see the sawtooth waveform here in the screen. Okay, so similarly, all the waveforms can be verified by giving appropriate codes and by selecting proper ports. Okay. Do you want to play this video once again? Any one of you? Can you able to understand or you want to play this video once again?